This short video provides a simple overview for how to write control plans. When writing a control plan, we need to consider the production process and put the steps of the production process, the sequence, in order. Those numbers, that order, must be keyed to the FMEA and the PFMEA to make sure that the two are consistent. There is information from the FMEA that you will need to write the control plan. It will have designation of special characteristics, and there is a place inside an FMEA where controls for production can be recommended. We need to make sure that those get included in the control plan. We also need to establish and specify the stations, jigs, devices, and tools that must be used. Those need to be identified very clearly. In this very simple example that we're going to continue to use throughout the video, the assembly station is listed as A102. We don't just say assembly station. We have to have the actual identification for it, just as we can't say a jig or a device or a measurement instrument. We need to say specifically which one, so it would be very clear to anybody else coming across this process at any time. If we come then to product and process characteristics, it's a very common thing for people to only put product characteristics in here, but you have to consider very carefully what the process characteristics are that we want to monitor. In this case, we've talked about assembling a plate to a base at our assembly station A102, and that we need to measure the screw torque. And we've said the screw torque is a class C special characteristic, means an important critical to quality characteristic in our system. Those special characteristics come directly from the FMEA. We don't have to determine them when we're writing the control plan. They've already been determined for us. Then we list the products, process, specification, and tolerance. Again, we need to be specific. So we need to say exactly what the number is, what the unit is, and what the tolerance is. For visual characteristics, a common mistake is just for people to say visual. No, there needs to be a visual standard, a limit sample, a visual standard, a go, no go, something to give an operator and a quality person or whoever guidance on deciding and identifying what's good and what's bad. Those visual standards must have specific controlled identifications. Those visual standards should be controlled documents inside your quality management system. So they have to have a unique identification number. So consider layers of controls. For example, we measure the screw torque. We do that 100%. But how do we know the automated station is correct that does the screw torque? Well, we have masters. We have masters at different levels that we can run. We can run them at the beginning of each shift to make sure that those masters are correct. Then we know that the measurements that we're getting from the station can be relied upon. We also want to put in logical levels of layers of controls. Sometimes redundancy is a good thing inside setting up quality systems and control plans. So a master's check at the start of the shift, and then we can have the automatic reading 100% for checking for cracks after the assembly. We have an established visual standard. We know what's good and what's bad. Okay, and the operators can check that 100%. But then we can also have quality people or someone else come along and check visual versus the standard, 3 pieces an hour, or do a control chart of some kind in order to layer that. A really important characteristic should be checked in a couple different places, in a couple different methods, in a couple different ways to make sure that we have redundancy in the system. So if an opportunity to come along where an operator didn't understand a characteristic, if there was some problem, if there was something different, there's another layer of controls and checks there to help us to see it. This can be done with manual checks, can be done with automated checks, can be done with anything. Layers of controls is a very, very good and effective strategy in a control plan. Then we come across size, frequency, and then control method. Control method is just the record. It is not a checklist. A checklist is not a control method. So often we see in processes all of the steps of the process or all of the checks that are supposed to be done listed in a row on the left, and then off to the right is a time or an operator's initials or whatever, and then check marks by everything, just to show that everything's done. This is a completely useless and meaningless activity, and you should never do it. The control method needs to include the actual data. It can be a station log, it can be a Pareto report, it can be a QC log, but we have to include the actual data. For a small sample size, 3 an hour, 5 an hour, something like that, we can write down every single dimension, every single measurement, every single variable. If something's done 100%, we certainly need to at least record every single defect so that we can see and react to it and know. These are very, very important control methods. If the inspection result is not recorded, the inspection is not done. Repeat, if the inspection method, inspection result is not recorded, the inspection will not be done. It becomes too easy to bypass, too easy to shortcut. We need the actual data from what we're checking. If it's important enough to record the data. Then finally, reaction plans, and this is the big part that is often missed. And people say, notify supervisor, notify supervisor, notify supervisor in this column, and it's not sufficient. It's not, notifying is not an action. So we need to be very considered and very careful in what we put here. We often see on 100% checks that they can't have 3 in a row. This is just silly. It just doesn't make any sense. So, 2 out of every 3 can be bad, but that's fine. That is ridiculous. So we need to think and base upon logic what those reaction plans will be based upon results. For example, if it fails the master check, we can't start production until the master unit passes. That's simple. Makes sense. For the automated readout, we have an and-on light that tells us if it's red or green, if it's good or bad. We stop production if the failure quantity exceeds 3 on any shift. That could be based very easily on previous performance, on what the reject history has been to help us identify any kind of an abnormal, out-of-control situation. Continued production requires, for example, the approval of the production manager. For the 100% check, perhaps based upon the failure history and the records, we say that we can have no more than 5 in a shift. And if we want to continue production, it requires production supervisor approval, maybe a different level, a little bit lower, a little bit different. And then on QC checks, a really important thing is to make sure that they take results back to operators, that we don't want quality people or other auditors doing checks and not sharing the results with the production people that do the 100% checks. We need that communication in place and then appropriate reactions. Again, I think of all these things, the reaction plan is the most important and often the most neglected.